Hello, and welcome to the first of our lectures on routing in data networks. This lecture uses material from the textbook by Shrikant and Ying, and some material from the textbook by Dijkstra and Gallagher. Now, routing, as many of you know, is a network layer functionality. Classically, the network layer is responsible for getting packets from sources to destinations across a network. So the network layer must know the topology of the network in some form and be able to make decisions about the routes taken. The network layer can provide either connection-oriented or connectionless service. Datagram routing, which is most common in the internet today, is a type of connectionless service where the routing decision is made once per packet. Accordingly, two packets of a user may follow different paths. That is, two packets in a certain transport layer connection may be following different paths. On the other hand, in virtual circuit routing, a path is created before sending packets, and the packets are delivered in sequence. This is the case in some connection-oriented services where flow control is provided automatically. In the rest of our discussion, we will be focusing on connectionless service, in other words, datagram routing. Now, in general, packets may need to take multiple hops to reach their destinations. So routing algorithms are responsible for deciding which output line a packet should be transmitted on. In the case of a datagram, independent decisions are made for each packet. Now, desirable properties of routing algorithms can be listed as the following. First of all, correctness. A routing algorithm has to work correctly. It should be simple in terms of computational complexity, robust, meaning it should be able to adapt to changing topology and changing demand. It should have stable operation, meaning it should converge. The routing tables should converge in a reasonable amount of time. And finally, one could talk about the fairness of a routing algorithm in terms of the rates allocated to different routes, or the optimality of a routing algorithm, which are often contradicting goals because the network-wide optimality may be starving some connections, some users. Now, a good routing algorithm will minimize delay for a given throughput under low load so that the flow control algorithm can allow more traffic into the network and increases throughput for the same average delay under high load conditions. So in classical network algorithm design, the two parameters that are the two essentially key performance metrics that are the two dimensions of the design of our algorithm are the throughput and the delay, and they are often conflicting goals. Okay, so a good routing algorithm will provide a good throughput delay curve. What is throughput? Throughput is the load that is offered into the network minus the rejected load, meaning the load that is correctly served by the network. Now, routing and flow control interact in a very complex feedback mechanism, and it will be the topic of our discussion in the rest of the chapter after we talk about routing. Note, however, that the classical network design metrics throughput and delay are currently being replaced or supplemented with more semantic metrics such as the age of information. This redesign is key to machine-generated data and machine-type applications, which are important components of 5th and 6th generation data network architectures. Now, in the rest, we'll talk about shortest path algorithms. There's a typo here. Shortest path algorithms. So we'll make it quite simple. We'll talk about routing basics essentially. We'll consider a directed graph where edges have directions. The cost of a link is specified for each link in the network, and we'll often assume that the links are bidirectional and the cost on a link is the same either way. This cost could be, classically the delay on a link, but it's not necessarily delay. It could refer to any cost that you would like to associate with that link. Now, assuming costs are fixed, our problem is to find the shortest path. In other words, the minimum weight path from a node to a destination, or from all nodes to a destination. Now, shortest path algorithms are mainly based on the following very simple optimality principle. It's the following. Consider a node I who wants to send data to node K. Now, the optimal route from I to K passing through some other node J can be obtained by concatenating the optimal route from I to J with the optimal route from J to K. Okay, this holds for all topologies and all optimality objectives as long as the costs are positive and additive. Why is this true? Let's define R1 as the path segment from I to J, and R2 the path segment from J to K, and R is the concatenation of these two segments. Okay, now if there was a better route from J to K, let's call that R2 prime, then we could have used R2 prime to improve the total route from I to K by concatenating R1 by R2 prime, which contradicts with our assumption that R was originally optimal. Okay, so to show you an example from real life, let's see. Suppose I'm trying to drive from point Z to point M, and I know that the shortest route from Z to M, I know, for example, that the shortest route from point A to point M passes through point K. Okay, then if I know that my optimal path from Z to M passes through A, okay, then I know that my optimal path from Z to M will also pass through K. This is obvious, I'm sure, to everyone who uses map applications when finding their way. Okay, now some consequences of the optimality principle are the following. There cannot be loops on optimal paths from all nodes to a given node. Hence, optimal paths from all sources to the same destinations for a tree rooted at the destination, they form a tree. So, for example, consider node B and the optimal routes to all other nodes in the network. These will have to form a tree because by the optimality principle, if there was, for example, a better way to go from B to I that does not go through C, this would have formed a loop here, right? But by the optimality principle, it does not. So packets, so since it's a tree, packets can be delivered to the whole network in bounded time. Now, given the topology of the network and the weight of the links, the problem of shortest path routing is to find the shortest path from source to destination. We will study the two main, most common shortest path algorithms, namely Dijkstra's algorithm and the Bellman-Ford algorithm. The basic difference between these two algorithms is their average and worst case complexities. So in this lecture, I will talk about Dijkstra's algorithm and we'll talk about the Bellman-Ford algorithm in the next lecture. Now, Dijkstra's algorithm is a type of link state routing. Nodes are supposed to know the topology network, meaning the weights of all the links and all the links in the network in relation to each other. The goal is to find the shortest path from the source to the destination. Here's how it goes. This is the algorithm. Suppose we have a node U. Okay. Now, node U wants to compute the distance, the optimal paths from itself to every other node in the network. And it knows the cost of all the links ij, Cij, for every link ij that is in the graph, in the network. It starts by initializing this set kappa as itself. The set kappa is going to hold the set of nodes whose, to which the optimal paths from U have been set. Okay, now here's how it goes, the algorithm goes. For every node in the network, initially, node U computes the weight of this node, meaning the total cost to this node, as WUI equals CUI if there's a direct link from node U to node I. That is, if node I is a neighbor of node U. Okay. Otherwise, if node I is not directly attached to node U, that is not directly reachable from node U, its distance, WI, is set to infinity. Okay. Next, we go and set PUIs. The PUIs will be the previous hop nodes when we're trying to go from U to I. Since this is the initialization, the previous hop nodes for U are U if the node I is a direct neighbor of node U. Okay, so if node I is a neighbor of node U, then PUI is set to U itself. Otherwise, the previous hop neighbor is currently not known, so PUI is set to -1. Okay, now after this initialization step in lines 3 through 6, we start the iterations of the algorithm. Okay, now we iterate on the number, on the size of the set kappa. And the way we do this is, in every iteration, the set kappa grows by one more node until it includes all the nodes in the network. Remember, it was initialized as the node U itself. Okay, so in this iterative step, we first go and find a node I star that currently has the minimum distance WUI out of all nodes that are currently outside of the set kappa.